So today we're going to continue talking about rebound ratios and heights we use from dropping the balls and the whole ball scenario. So yesterday we found the relationship between the height and from which balls bounce and its rebound height can maintain a constant ratio. So ours didn't quite, because we didn't actually continuously do it. So we watched it bounce once and we didn't do it. So what we're going to do today is consider the fact that if we were to bounce it, it would continue at a constant ratio. So thinking about what we did yesterday. So here, when we were talking about the rebound ratio for the team's ball, we're going to use the first height, the 100, dropping from 100 centimeters. And in one class period, in second period, we said 70 centimeters back up. And in the second class period, we said that it bounced up to 72. We're going to go ahead and use 70 over 100, just because that's going to be good enough for us. So our rebound ratio is going to be 70 over 100. And so the height we dropped the ball from affect the ratio. And yeah, it changed depending on where we dropped it from. The lower we dropped it from, the less bounce it back it had because the decimals got smaller. But it was, they were all within a reasonable margin of error there. So it did a little. So yes, a little. That is an LI, not an L squiggle. That was terrible. Let me try that word again. There you go, a little. If we use the same ball again and drop it from any height, can we predict its rebound ratio? And I would say that, yeah, probably. I mean, it's going to be about 70 over, like, a relationship of 7/10 of the original height. So we could take this and times it by the starting height, and that would give us our new thing. So just kind of keep in mind that we're using multiplication here, and it's not perfect, but it's kind of the whole point is that this relationship, that it's a ratio, not a sum. And so it doesn't bounce up to the same, like we're not subtracting the same number every time. Like we subtracted 30, so now we'll subtract 30, so the next one only makes it to 10. It's not quite that clean, but that's the basic idea. So we're going to do 6 successive bounces starting at 20. So bounce number 1, bounce 0, excuse me, start with bounce 0 is 200. Bounce 1, if we do the 70 over 100, will be, let's just go with 0.7 for our rebound ratio is 0.7. So 0.7 times 1 times 200 will be 140. Let me just double check that math. 200 times 0.7. Yep, 140. Keep this calculator here in case I need it again. So then 2, and we're going to times 140 now by 0.7. And now we get 98. By the way, this is why I chose to use the 7D instead of the 72. Makes for easier math. We're going to times that number by 0.7. And so 3 will be 68.6. And then we'll times that by 0.7. And so that's 48.02. And we will times that by 0.7. And that's 33. That 3 does not. 33 times 0.614. And then our final bounce. Sixth bounce will be 23.5298. In this situation, our independent variable, and I'm going to type this because my fingers are not doing great today with the writing, so I'll just type it. 16 is probably fine. So the independent is the bounce, and the dependent variable is the rebound height. So those are our two things. That's the answer to part D. Let's go ahead and create a graph. Our graph should be discrete because we aren't tracking the path of the ball. We're just tracking the bounces. Because if we're doing the path of the ball, then we might connect it. But since we're just doing bounces, we're going to leave it disconnected. So that's how you can tell. Since we're tracking the height bounces, not the whole path, we're just going to do these discrete events that happen that aren't really connected things. So I'm going to go ahead and let Desmos do this graphing for me. Let's see. Bring this in. Desmos calculator, make a table. And so 0 was 200. 1 was 140. 2, 98. 3, 68.6. 4, 48.02. 5, 32, I think. Nope, 33.614. And last, 6, 22, 23. I don't remember. I'm not just getting annoying. .5298. Okay. So anyway, those are my numbers. Now I can't really see anything very well. So I need to change my window so I can see it. So click on my wrench. I need to change my x-axis. I only need -1 to, let's go to 6. 10 is fine. Y-axis, I don't need any negatives, but I need to go all the way up to, let's go to 10. And there's my path. So you can see how if nothing affects the ball, this is what should happen. We were talking about this yesterday with the drop, bounce up here, drop, bounce up here, drop, bounce up here, drop, bounce up, and so on all the way back until it starts to just lose its momentum and it doesn't bounce, it starts to roll. So that's your basic idea behind it. So go ahead and do your best to get this graph onto your paper. You might want to freeze the screen here for a minute. Get that graph on your paper. You'll notice that here we're counting by tens as we go up to 200, or you can count by 50s. Makes it easier, whichever one works best for you. And so now we have our graph. We've got our things. We've answered all the questions. Our next portion is this. A function can be used to model the data from problem 529. Compare your graph of successive bounces to the graph for type versus bounce we invested. And the other one is different. We can use the same family. So remember, we tried to do the line yesterday and it just didn't really seem to make any sense. So we had to switch. We talked about how we would probably have to write the other equation. And yes, we're going to be using exponential functions here. The difference being that yesterday, since we were dropping from different heights and just recording that first bounce back, yesterday's would be an increasing, because we had our points went backward. We did 200 or 171st, and then all we did them, but when we plotted them, they all went this way because we had our x-axis was the starting height and the y-axis was rebound height, and now we have bounce number and rebound height, and so that changes things. But they're both exponential functions. The pattern of growth for successive bounces is same with different other models. It's the same because we're talking about the bounciness of the ball and that rebound ratio. I'm going to go ahead and give you the equation for this, and it is a little bit strange, so I'm going to go ahead and jump over to my math writing tool. When that gets open, it's thinking about it still. So here it is. Let's squish that up and put it on the screen. So this is an exponential function. Our starting height goes first, so 200. So our starting value, just like with other things where we have a starting number, our rebound height, 0.7, goes inside the parentheses because that's the number we're using over and over again. Remember, it's called an exponential function. So we have our starting value, our multiplier, our rebound ratio, and then an exponent because we use the rebound ratio over and over and over again. So this is our equation. Y equals 200 times 0.7. I'm going to put the 0 in here. 0.07 to the x power. And yesterday's it would be a little different because we would be going the other way, it was increasing. And so instead of being 0.7, it'll probably be 100 over 70. And so that would change it a little bit, our fraction. But that's the idea. Go ahead and record this function onto your paper. Y equals 200 times 0.07. So y equals 200 times 0.7 raised to the x power. Starting value, rebound ratio, ratio being the key word here. So the ratio is really important in this sentence. And then describe the growth pattern of growth for successive bounces is the same as different from other models. It is the same because it's multiplying, and that's what we started with on Tuesday. It is different because we've been adding forever, but it's the same because it's the same number. So with all of our line patterns, we were adding this or subtracting the same number every time. And with this exponential pattern, we are multiplying by the same number every time. Come back, keep watching the playlist so that you can see the homework hints, because we are finished with today's and we're on to homework next. So homework hints will be in the next video. Have a nice day.